Welcome to Math 90. I'm Professor Ridge, and today's lesson we'll be covering 1.1, some basics of algebra. Here are the topics we'll be covering in this section. So we're going to start off with algebraic expressions and their use. So first off, we'll start off with some definitions. So what's a variable? A variable is any letter or symbol that represents a number that can vary, that can change, hence a variable. So variables, the value of variables can change. Okay, now sometimes we use letters or numbers, or letters or symbols to represent something that doesn't change. We call that a constant. So any letter or symbol that represents a number that stays the same. We'd say a fixed number or constant. Okay, so variables, again, any letter or symbol that for a number that can change, a constant doesn't change. So some examples of constants would be that you're probably familiar with is pi. Okay, so a lot of times we'll write pi, and what that represents is the number 3.14159 something 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 forever and ever, and this is just an approximation. Once you stop writing, then approximate. So pi is the exact number. It's actually an irrational number, which we'll talk about in a little bit. Another example of a letter we use for a constant is the exponential number, 2.718. Same thing. So those are two examples of constants. Okay, so our next vocabulary word here is an algebraic expression. Zoom in just a tiny bit for you there. So an algebraic expression consists of variables, constants, numbers, operation signs. So those are like add, subtract, multiply, divide. Those are the four basic math operation signs. Of course, we have others. So algebraic expression consists of variables, constants, numbers, operation signs, and or grouping symbols. Okay, let me give you some examples here. So it could be any of those by themselves could be an algebraic expression. So it could be simple as just a number. Right? That's an algebraic expression. Not very exciting. Maybe you can do some numbers and letters. Okay. You can do something like 4w minus 8, a little more complicated. And even 17x squared plus 3x plus 5 over x cubed minus 8. Okay, so those are all algebraic expressions. Now, an equation is formed when we place an equal sign between two expressions. So an example would be, we could take like 4w minus 8, put an equal sign. Oops, sorry. So we can do 4w minus 8 equals, just put a number over here. And I'm sure you're familiar with how to solve that. We'll talk about that later. Okay, so there you go. So our next topic is our next topic is we're going to be translating to algebraic expressions. So we can take, here's some keywords for translating. Addition, add, sum of, plus, increase by, more than. Subtraction, there you go, you can read those. Multiplication and division. So the one I want to talk a little bit about is this structure here, the sum of, difference of, product of, quotient of. Now all those, the sum of, difference of, product of, quotient, those all are the result of adding two numbers, subtracting two numbers, multiplying two numbers, dividing two numbers. So if I were to translate this phrase, I don't know if I've mentioned earlier, but I am basically teaching just like I was in the classroom, going a little bit faster with the idea that it's being recorded. You can hit pause to kind of keep up with me. But anyway, I'm trying to recreate the feel in the classroom. Okay, so the sum of two numbers. So we can start off with something simple like that. And basically the way you would translate it would be x plus y. I could also say the difference of, instead of saying two numbers, I can tell you what those two numbers are, or tell you one of them and say some other number. So the difference of some number and 8, I would write as x minus 8. Okay, now the structure, see this difference of, and if I'm going to be more explicit about the two numbers that are being applied to this operation, so difference would be subtraction. It goes where the word where and is. If I change that to product, then you would make it that multiply. If I change that to sum, that'd be plus, and quotient, that'd be divided by. And then of course you can get a little more complicated with, you can make this another phrase itself. So I can say the sum difference product. You can even like nest them. In fact, let's do that right now. The product of some number and the sum of another number and 7. Okay, so basically, so I got this product. So here's the two sides of that operation, and then basically on the right side here, you have this whole phrase. So it's going to be some number, which will make x, and that's times. Now this is a phrase, so I gotta translate this. So this is the sum of, so it's that same structure. So I'm going to put a parenthesis. and then another number, so we'll make that y, and that's being referred to by the sum, so that's going to be plus 7. Okay, so you can make it a little more complicated like that. So that's the product of some number and now we talk about the sum of another number and 7. Okay, there you go. Okay, a couple more I want to talk about. If I were to say 8 more than some number, and whenever you see the than, more than, less than, that actually switches the order. Now for addition, it's not a big deal. Okay, so some number plus 8 is the way that would be translated to. So whenever you see the more than, less than, technically it switches the order around. This part will come first, and then the first number would be last. So it'd be x plus 8. Now again, mathematically, because of the commutative property, addition's commutative, meaning you could switch the order and you'll get the same answer. So if you wrote this, I probably wouldn't mark you wrong, although technically the first one's the way it's translated explicitly. All right, but now with subtraction, it's a big deal. So if I said less than, that would be subtraction. So you have no choice. You have to make sure you do this right. This one's going to be first. So let's use W this time. Less than is minus, and then the 8 comes next. Okay, so that's 8 less than some number. Now I can make it a little more interesting. How about 5 less than the product of two numbers? So a little more interesting there. So again, here's that less than, so it's going to switch the order. This part's going to come first. This is a phrase. Okay, we can translate that. The 5 comes last. So I'm going to translate this phrase, minus 5. So what's the product of two numbers? And we know the product is multiplying, and we're going to multiply two numbers together. So xy minus 5. And that's the way you translate that one. Okay, now let's talk about exponential notation real quickly. All right, so the expression exponential notation. So the expression a to the n, in which n is a counting number, okay, so n is a counting number. Counting number we're going to talk about in a little bit. 1, 2, 3, 4, the numbers you use to count. Okay, so 1, 2, 3, not 1.5, not 3/2, 2/3. Okay, so in which n is a counting number means okay, so the expression a to the n in which n is a counting number means, so we're going to have a times a times a times dot 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 times a in factors. So that's a to the n. So basically the number in there is not the number of times you multiply it, it's the number of a's are in the product. So for example, a to the 5th means that I'm going to multiply 5 a's together. So there's 1, 2, 3, 4, 5 a's. Okay. So a factor is just a number that's in the product. So I got 5 factors of a. Okay, so when we place a variable with a number, we say we're substituting for that variable. The calculation that follows substitution is called evaluating the expression. So if we want to evaluate an expression, okay, before I do that, I like to kind of talk this way. So evaluate just means, I think of it as to get a value for. Okay, so that's what it means. So if I ask you to evaluate an expression, I'm asking you to get a value for that expression. Now to be able to do that, I need to tell you what the values of the variables are, and then you substitute them in and then do the math so you can get a value for it. So, example, if I said evaluate for x plus 5, and you can't evaluate it until you know what x is. So I would have to tell you when x equals, say, 7, and now you can evaluate this expression. You can get a value for the expression by substituting 7 in for the x, using order of operations to do the math here and get a value for it. So we know that we do inside parentheses first. Well, there's nothing to do in there. Exponents next, and then we multiply from left to right, so that's 28, and then multiply and divide from left to right, and then add and subtract. So 28 plus 5 would be 33. So the value of this expression for x plus 5 when x is 7 is 33. So that's evaluating the expression. Okay, let's review the order operations real quick since I just mentioned them. So here's our rules for order of operations. So our first level, so you think of this as a level, so precedence. So your first level, first precedent would be to simplify within any grouping symbols. And I can hear some of you already saying, please excuse my dear Aunt Sally. We'll talk about that in a second. But the problem with that is P is for parentheses, but it's more general than parentheses. It's not just parentheses, it's all the grouping symbols, which parentheses are one type of grouping symbol. So the other ones are, you got parentheses, brackets, and usually when you have nesting parentheses, you use parentheses for the innermost one. Brackets would be outside those. Braces. And of course the big fraction bar. That's another grouping symbol. It groups into a numerator on top and a denominator on bottom. So the fraction bar is also a grouping symbol. All right, so that's your please, parentheses. But remember, it's more general. It's all the grouping symbols. Excuse. That's my exponents. So you're going to do all your exponents. Simplify all your exponents. Now here's another problem with that acronym. Please excuse my dear Aunt Sally. Multiply and divide are on the same level, not multiply first, then divide, and it's not divide first, then multiply. It depends on the question, on the problem. It's the tiebreaker. They have the same level of precedence, and the tiebreaker would be left to right. So you're going to simplify, perform all the multiplication and division as either occurs working left to right. Okay, so multiply or divide, and you just look at the problem going from left to right. If you see a multiply, do it. If you see a divide, do it. And you just keep continuing until you go all the way from left to right. And then 4, that's at Aunt Sally. And again, same thing. Adding and subtracting are the same level of precedence, so you don't necessarily do one before the other. They're tied, so the tiebreaker is left to right. Okay, so I'm just going to write that. Perform all add, and at this point, that's all that should be left. From left to right. And it's just like up here as the either occurs. One more thing I want to point out, when you're inside grouping symbols, you still follow order operations. So inside a parenthesis, if there's another set of parentheses, you're going to work in there first. Okay, so you can have 15 sets of parentheses nested in each other, and then you're going to start with the innermost parenthesis first. All right. Okay, so the next thing we want to talk, well, actually it's our last thing we're going to talk about for this lesson is sets of numbers. So what do we mean by sets of numbers? So we kind of used some of the vocabulary already. We have, basically it starts out with counting numbers, or we say natural numbers. So here we go, sets of numbers. So your first set is natural numbers. And actually, this book will use some symbols for it. And so natural numbers are the same thing as counting numbers. Some people refer to these as counting numbers. Some refer to them as natural numbers. And basically, if you think about the development of the number systems, this would be the first naturally occurring sets of numbers, is because the first thing we probably needed numbers for was to count. You know, we needed to know how many whatever was that we wanted to know. So anyway, so that's probably the first set of numbers that naturally occurred would be the counting numbers. And again, when you count, so here's the set. So this symbol is for the brace is for set. 1, 2, and again, when you count, you don't start at 0, you start at 1. 1, 2, 3, 4, 5, so on. Okay, so that's the counting numbers. The next set is whole numbers. And basically, the only thing is different about natural numbers and whole numbers is the addition to 0. And it actually took quite a bit of time between when counting numbers were developed to when just to have a symbol for 0. That was actually a big leap in human thought, believe it or not. Okay, so that's the only difference between natural numbers and whole numbers. So if we're talking about whole numbers, it's the counting numbers plus 0. And then integers, and those are, it's the set of it's the set of whole numbers and then the opposites. So it's going to be -3, -2, -1, 0, 1, 2, 3, so on. It goes in both directions forever. Okay, so that's the basic sets of numbers. The next thing I want to talk about before we finish off with the sets of numbers, because we still have to talk about rational numbers and irrational numbers. But before we do that, I want to talk about this notation here. So when we're talking about sets, we use two types of notation generally. There's what's called roster notation. I always talk about in class, like if you were to think about a roster, what comes to your mind? And you know, you can think of baseball, like the roster is the list of everybody on the team. I have a roster for the class, and your name would be on it somewhere. So you're explicitly listing each member of the set. So an example would be, here's an example. So if I want to say all the whole numbers between 1 and 7. So between would be 2, 3, 4, 5, 6, and I explicitly listed out that set. Okay, so that would be roster notation. Now, set builder notation, sometimes it's impossible to use roster notation because you can't list them all out. Here it's implied, so this still would be roster notation. But even for some other sets, it's impossible to actually list out all the members. So we have this set builder notation. And basically, you use set builder notation, you describe what it means. You're going to describe or give a rule for what it means to be a member of the set. Okay, so the way I could have done this setup here is basically, I'm going to say the set of all x's such that x is a whole number between what did I say, 1 and 7. So see, I'm describing it. And again, so the braces is the set. The straight bar is such that. So it's a set of all x's such that x is a whole number between 1 and 7. Okay, so that is a set builder notation. So that's such that. And then again, the brace tells you it's a net, it's a set. So the way you would read this part is the set of all x's such that x is a whole number between 1 and 7. Okay, so this set and this set are identical. Set builder, roster. Okay, so we took that little side journey so we can go back to our sets of numbers, because the next set, back up here we were talking about integers. Now, what if I needed to describe like what's in between 1 and 2, like 1.5 or 1/2 between 0 and 1, 2/3, so on. Well, those are called rational numbers. And rational numbers, we can't explicitly list all those out. It would be impossible to. So we needed this roster notation. Rational numbers so numbers that can be expressed as an integer divided by a non-zero integer are called rational numbers. So here's the way we write it. It's a set of all p over q such that p is an integer. Integer. Q is an integer. Normally I write p and q are an integer, but this is okay. And q is not allowed to be 0, because we know that anything divided by 0 is not a number. It's undefined. Okay, so that's the way we describe the rational numbers. So it's basically anything that, so in words we can say any number that can be expressed as a ratio of two integers. Okay, so this is the same thing using set builder notation. So an example would be 3/5. So that's 3 is an integer, 5 is an integer, and that's a ratio of two integers. So 3/5. Now the key thing is can be expressed, so it doesn't have to be written as a fraction to be a rational number. We know a whole number, we can take any whole number and write it as a fraction. We can write it as 5 over 1. So 5, even though 5 is a whole number, it's a natural number, it's an integer, and it's also a rational number. Okay, so because we can write as a ratio of two integers. 1.3, well, we can write that as 13/10. So 1.3. So basically, and then 0.3333 forever, well, we know that's 1/3. So basically any non-repeating, non-terminating decimal number can be written as a fraction. So any non-repeating, non-terminating decimal number is also a rational number. Okay, so fractions, ratio of two integers. Now irrationals, we just describe them as things that can't be written as a ratio of two integers. Okay, so irrational numbers so numbers that are numbers that cannot be expressed as a ratio of two integers. Okay, those are called irrational. Okay, so some examples of those, we talked about them earlier, those constants. Pi, that's an irrational number. You cannot write it as a ratio of two integers. 22/7 is not pi, it's an approximation of pi. So pi, e, again that number 2.718. See, it's a non-terminating, non-repeating decimal. It goes on forever and ever. There's no pattern. That's irrational. Most of your square roots that do not simplify are irrational. So square root of 2, 1.414, again, goes on forever and ever. So, you know, if you had like square root of 9, that simplifies to 3, which would be a rational number. Okay, so square roots that do not simplify are irrational. All right, so just to kind of look at the sets of numbers, how they nest. Oh, I forgot to tell you, we'll write this down. So real numbers are basically everything that we're going to deal with in here. If you take all the irrational numbers and all the rational numbers, you get the real numbers. So real numbers are either rational or irrational numbers. I'm not going to write that down. Okay, so we can kind of see how these numbers built. So we start out with the natural numbers. We adjoin 0 to it, you get the whole numbers. You do the opposites of these numbers, put them together, you get integers. And then you put in the fractions that don't simplify to integers. Put those together, you get the rational numbers. And then the irrationals are not rational. Put those together with the rationals and you get the real numbers. Okay, so that's the sets of real numbers. And I believe that concludes lesson 1. All right, so now go to My Math Lab and try to complete the exercises for section 1.1, and then come back and watch 1.2. Hopefully it'll be posted soon. All right.